This is AP Calculus 2-6, derivative rules, and today we're going to talk about the constant rule, the sum and difference rule, and the constant multiple rule. First of all, we're going to talk about the derivative of a constant. Now remember, a constant is just a number that stands alone. It doesn't have any variables. So 5 would be considered a constant. It doesn't have any variables. Now understand, if it doesn't have a variable, the variable would be understood to be x to the 0 because x to the 0 is 1 and it would cancel out. So if you think about it in terms of having a variable, and our variable would have to be x to the 0, if we use the power rule on that, 0 times 5 would be 0, and then if we decrease the exponent by 1, we would have 0 times x to the negative 1. And so if we have x to the negative 1, that it would be on the bottom, but if we have 0 times that, wouldn't it just be 0? So the derivative of a constant term is always going to be 0. So if they give you the function f of x equals 2, well, the derivative of that, or f prime of x, will be 0. And that's always going to be the case. And then that takes us to the sum and difference rule for derivatives. Most of the time in math class, we're not going to be dealing with monomials only. We're going to be dealing with polynomials, where we have several monomials added or subtracted from each other. So if we have a polynomial for our function, we need to be able to take derivatives of that as well. And it's really not any more difficult than doing a monomial. You're going to take the derivative of each individual term separately and have another polynomial that is 1 degree less than the polynomial that you started with. So for a function like this, if I want you to find f prime of x, all you have to do is find the derivative of each individual term. So 2 times 3 is 6. If I decrease the power of x squared by 1, I would get 6x. 2x to the first, 1 times 2 is 2, and we would have x to the 0. And then the derivative of a constant, remember, is always 0. So the derivative of this function is 6x plus 2. If you look back in your notes from when we did the limit process, I believe this was one of the first problems that we did that way, and we did get 6x plus 2 when we did it using the limit process. For this one, we've also done this one using the limit process in our notes at some point. If we take the derivative of that, we would have f prime of x equals 4x, and it would be plus 0, so we just leave 4x. So the sum and difference rule, it doesn't matter whether you have a plus or a minus in between your terms. You take the derivative of each individual term separately, and if your derivative ends up with a coefficient of a negative, you would put a minus in front of it. If it ends up with a coefficient that's positive, you would put a plus in front of it. It is that simple. So here I have a few more examples that I want to do with you, and then I'm going to let you do a couple on your own to see how you're understanding. With this first one, if I want to find the derivative of that, f prime of x, I'm going to take the derivative of each monomial separately. So x cubed, the derivative of that would be 3x squared. 2x squared derivative would be 4x. The derivative of minus 3x would be minus 3. The derivative of 10 is 0. So the derivative there is 3x squared plus 4x minus 3. In this one, the first thing I'm going to do here is I'm going to do the math of that monomial on the bottom. So if you look at that, I'm going to go ahead and say that that is 5 over 8x cubed. And if that's the case, then isn't that 5/8 times x to the negative 3? And so then I can take the derivative of what I've got left. So f prime of x, negative 3 times 5 is negative 15 over 8. And then that x is going to be to the negative 4 because we decrease the power by 1. And then we have f prime of x equals negative 15 over 8x to the fourth, because we can't have a negative exponent left in our answer. For this one, I'm going to rewrite that one first. So still with the sum and difference rules, you do still have to rewrite your function sometimes. So if I do that, I have f of x equals 3 times x to the 1/2 plus 5. So f prime of x is going to be 1/2 times 3 is 3/2 times x, decrease that power by 1, that's negative 1/2, and then it'll be plus 0. So f prime of x is equal to 3 over 2 times the square root of x, and you can leave it like that. You could also write that as 3 over 2x to the 1/2. That would be fine as well. So I've got 2 more down here on the bottom. Go ahead and pause the video, see if you can get those 2 done on your own, and then we'll talk about the answers. Okay, so I've done these. In the first step for this one, when I take the derivative, 2/3 times 1 is 2/3, and then I have x to the negative 1/3 because I subtract 1 from 2/3. Then the minus sign, 1/3 times negative 3 is negative 1, so minus x, and then 1/3 minus 1 is negative 2/3. And then 1 times 3 is 3, and the x drops out. So this is what I have with your initial derivative, but remember you're not allowed to have any negative exponents. So then I put those negative exponents on the bottom. And you are fine to leave it like this. When you were in Algebra 2 and probably in pre-calculus, your teacher probably didn't allow you to have fraction exponents in your final answer. But at this point, it's okay to do that now. If we try to get rid of every fraction exponent from this point on, sometimes the work gets so tedious that it's too difficult to do that. So from now on, if you have fraction exponents, it's okay to leave them like that. Just don't leave them negative. We can't have negative exponents. That's still going to hold true. In the next one, that one's a little bit simpler than the last one was because you didn't have any fraction exponents to deal with. 3 times 4 is 12. Decrease that power, it's x squared. 2 times 2 is 4, so it's plus 4. Decrease the power of x by 1, so that's 4x. And then this one would just be a minus 4. And of course the derivative of a constant is always 0, so that constant drops out. Next, I want to demonstrate the constant multiple rule. There's a rule in calculus that says if you have a function and that entire function has been multiplied by a constant, then you could do one of 2 things. You could distribute the constant first and then take the derivative, or you can take the derivative of the function part and then multiply that derivative by the constant, and you're still going to get the same answer either way. So I want to show you how that works. With this, if I want to distribute that constant, I can do that. And I can rewrite this as f of x equals 10x squared plus 15x minus 4. And then I could take the derivative, if that's what they're asking me to do. So if I take the derivative, I get 20x plus 15. Okay? But what if we had done that one a different way? What if I had had the original and I didn't want to distribute first? I wanted to take the derivative of what's on the inside and just multiply it by that constant at the end. Well, if I take the derivative, I'm just going to keep the 5, and then I'm going to take the derivative of the function part. So 2 times 2 is 4, so that'll be a 4x plus 3, and then the 4 drops out because it's a 0. If I then distribute the 5, I should still get the same answer. Okay, so it doesn't matter whether you distribute to begin with and then take the derivative, or you take the derivative and then multiply by the number on the outside. Depending on what they give you, and we're really, right now we're only doing polynomials, so I can't really give you functions where you're not going to want to multiply yet. A lot of times you don't want to multiply first. You want to take the derivative and then just multiply the answer by that constant. But it depends on what they give you. Sometimes, like in this one, it really doesn't make a difference. It's just as easy to do it before as it is after. But it's hard for me at this point to show you when this is useful, but you'll see it quite a bit later in the chapter. So let's do one more of those. If I give you something like this, and this is probably the only type of problem that I can show you that is one where you're not going to want to multiply by the 1/3 first. If you do that, now, since this is to the square power, I am going to have to square what's inside. So that would be 9x squared. And then if I take the derivative, I'm just going to keep the 1/3 in front and take the derivative of the inside part. So that's 18x. And then multiply by 1/3. So I would get 6x. So really with polynomials or monomials, that's the only way I can show you this with one that's a little bit more complicated just because it had the square outside. But when you get into the natural log functions or any of those transcendental functions that we'll talk about later, that 1/3 in front or the 5 in front, whatever the coefficient is, you're going to want to wait and take care of that later or just bring it down as part of your answer rather than trying to distribute everything. It just complicates things if you try to do it before you take the derivative.